Let everyone know they are being recorded. Okay, it means we are recording. Okay, so let's start. We're still in chapter 4, exponential and logarithmic functions. What are we doing here? We are modeling with exponential functions. So at this point, means you understand the exponential functions, and we're going to use them to model real life situations. So the objective is to know the exponential growth. The objective is to learn about the exponential growth related to doubling time, exponential growth related to relative growth rates, radioactive decay, and Newton's law of cooling. Now, let's say many processes occur in nature, such as population growth, radioactive decay, heat diffusion, and numerous orders can be modeled using exponential function. In this section, we study exponential models. Now, let's look at the exponential growth. They say, suppose we start with a single bacterium, which divides every hour. After 1 hour, we have 2 bacteria. After 2 hours, we have 2 to the power of 4 or equals to 4 bacteria. After 3 hours, we have 2 to the power of 3 equals to 8 bacteria, and so on. We see that we can model the bacterial population after 3 hours by the function that. Are we able to see that we can model that population by that function, guys? Yes, no. So remember what was the question?
Yes, ma'am.
They
But
say,
can you just further explain, ma'am?
let me do that quick. I need a Word document. Okay. So now they say we start with bacteria. They call it a bacteria, this one, right? And they say every hour it splits basically into 2. So they say, suppose we start with a single bacterium which divides every hour. After 1 hour, we have 2 bacteria. After 2 hours, we have 4 bacteria. After 3 hours, we have 6 bacteria. Meaning that after 1 hour, we have 2. So this one becomes, it splits into 2 like this. Do you see that? This is 1 hour. Ne? In 2 hours, this will also split into 2 because it's doubling. And this will split into 2 as well. In 3 hours, do you see that this will split into 2, 1, 2. This will also split into 2, 1, 2. This splits into 2, 1, 2. And this splits into 2, 1, 2. Do you see the pattern, guys?
Yes, ma'am.
Meaning that at t is equals to 0, we had 1 bacterium. At t is equals to 1, we had 2 bacteria. At t 2, we had 4 bacteria. At t is equals to 3, we had 2, 4, 6, 8. We had 8 bacteria. If we take a look at this and look at the pattern here, you'll notice this. This is 2 to the power of 0, which is 1. This is 2 to the power of 1. This is 2 to the power of 2. This is 2 to the power of 3. Meaning that a function to model this relationship is what? It's f of t is 2 to the power of t. Because we said at t0, 0, we have 1. At t1, we have 2. So meaning that this is how we get the function. It'll be 2 to the power of time to get the number of bacteria. Does it make sense now? Yes, no?
Yes, ma'am.
Yes, ma'am.
Okay. So that's the function here. Now they say if we start with 10 of these bacteria, then the population is modeled by 10 times, what's this? 10 times 2 to the power of t to the power of 2 to the power of t. Meaning that here, we initially started with 1 bacteria. That will be times 1. So this is equals to 1 times 2 to the power of t. So if initially we have 10, it means it will be 10 times 2 to the power of t, because if you put t here at 0, you'll see you'll have 10, meaning initially you have 10. If you put t is equals to 1 here, you will have what? You'll have 20, like that, like that. Are we all together there?
Yes, ma'am.
Okay. Now they
Yes,
say
ma'am.
a slow. So now, thank you. They say a slower growing strain of bacteria doubles every 3 hours. Do you see that? Meaning that our bacteria is very fast. If it's doubling every hour, then it's very fast. But they're saying a slower growing strain of bacteria doubles every 3 hours. In this case, the population won't be modeled as this one. But then the T will be divided by 3 because it doubles every 3 hours. So then instead of having that, we'll have f of t is equals to 10 times 2 to the power of t over 3. Are we together? Guys, are we together?
Yes.
Okay?
Yes, ma'am.
So, okay. So now we then come to the exponential growth doubling. Since then you said you understand that part. It says if the initial, so the exponential growth doubling, this formula is only used when they say things are doubling up, basically. And it can also be used. Okay, let me not give you that clue first because I'm going to ask you a question. So now they're saying this formula is used when when they say the population is doubling at a particular time and whatsoever, then for you will use this one. Are we together? Are we together, guys?
Yes, ma'am.
We are together,
Yes,
ma'am.
ma'am.
Yes, ma'am.
Thank you. So exponential growth. Exponential growth, that doubling time. They say if the initial size of the population is n0, né? And the doubling time is a, then the size of the population will be this formula here. Are we together there?
Yes.
Guys? Okay.
Yes, ma'am.
So where A and T, look at this, A and T are measured in the same units. So every time, make sure you check if both A and T are minutes, hours, days, or years. You need to check that. If not, one has to be converted. Now, they say, under an ideal condition, a certain bacterial population doubles every 3 hours. Now, you see they're saying it doubles every 3 hours, meaning that we're going to use that formula that says n of t is equals to n0 of 2 to the power of t over a, which is this one over here. And they say doubling time is a. What is doubling time in our case? They're saying doubles every 3 hours, meaning that our A is equals to 3, right? Now our N0 is equals to what? Initially, there are 1,000 bacteria. So this is 1,000. All together, guys.
We are together, ma'am.
Yes.
So now
Yes,
they
ma'am.
say find a model for the bacterium population after T hours, meaning that your formula has to have T. So then we have that N of T is equals to 1,000 2 to the power of t over 3. And that's the formula. That's what they're looking for. Are we together there?
Yes, ma'am.
May I please have 3
Yes,
yeses?
ma'am.
Yes, ma'am.
Now they say, how many bacteria are in a colony after 15 hours? What do we do?
We substitute 15 to T.
15 to T, yeah.
Thank you. But the first thing is check. The doubling time is 3, right? And it's in hours. This is also in hours. Therefore, you can directly substitute 15 there. So this is 1,000 e to the power. Why am I liking e? So it's t 15 over 3. Always try to simplify it. So this is 1,000 times 1,000 times t to the power of what? T to the power of 5. And this one you can solve without a calculator, isn't it, guys?
Yes, ma'am.
Because
Yes.
this is 35, and then you know that this is 35,000. Okay. After how many hours would the bacteria count reach 100,000? What are they looking for there?
Looking for T.
For T.
Okay. So meaning that we're going to say n of t is equals to n0 2 to the power of t over 3. So they're looking for t. We know that n0 is equals to 1,000, and then n of t is equals to 100,000. So then we substitute and say 100,000 is equals to 1,000 e to the power of t over 3, right? Then over 1,000 over 1,000, and then this. Okay, let me erase here. We can see that this 0 cancels that 0, cancels that 0, 0 cancels this 0. Then it means this side it's 100. So this implies then, let me write like this. So it's 100 equals to e to the power of t over 3. So what do I do here? E to the power of t over 3. What do I do next? How do I solve that, guys?
We introduce log.
We introduce log.
Thank you. So then you say log of 2 to the power of 3 over is equals to 100. Sorry. Log of 100. And log of 100, it can be 10 to the power of 2. Are we together there?
Yes, ma'am.
Yes.
So now we know that this will be t over
Yes,
3
ma'am.
log of 2. Now this will be equals to 2 log of 10. So then this will be t over 3 log of 2 is equals to 2. Are we together or I lost someone?
We are together.
Okay. I need space here, so let's come here. So what did I say? Just need to go back to what I said. Okay, let me pull it here. So I said this is t over 3 log of 2 is equals to 2. Then this is t is equals to 2 times, this is t log of 2 is equals to 2 times 3. So this is t log of 2 is equals to 6 divided by log of 2 divided by log of 2. Then t is equals to 6 over log of 2. And that's the value of t. You can use the calculator for now, but in the exam, I want you can leave it like that. Anyone who didn't understand this part, guys? Anyone who didn't understand this part? Where? Hello? Guys, am I talking to myself?
No, ma'am. Ma'am, can you use the lean on this one? Can you work this one using lean, please?
You can't use a lane. I mean, okay, let's avoid two. You see, there's no, you see here, there's no E, right?
Okay.
So let's avoid to use the lane. If there's no E, avoid to use the lane. If there's no ln, use the E.
If there is E, then must use ln. Okay.
Yes, if you see there's an E, use ln. Otherwise, you always use the common log.
No problem.
If there's no E, okay? Are we all together? We even know how this log 10 disappeared. And we remained with 2. Yeah. Guys?
Yes, I know.
Yes,
It's
ma'am.
log base 10
Thank you.
and 10. It's 1.
Very much. So the population at T is modeled by that, where T is the time in hours. Were we supposed to do that? We did all the questions. So then after 15 hours, the number of bacteria is 32,000. That's what we got. When NT is equals to 100,000 in the model that we found in part A and solve the resulting exponential equation, this is what we get. This is what we get. And this is what we get, and this is what we got. You see, so in me, I'll do this. In the exam, your question will be like T is equals to 6 over log of 2. Not like 0, something, because remember, we're not using calculators, but you can simplify this, and then it will be approximately 19,93. So they say the bacterial level reaches 100,000 in about 20 hours. Are we together?
Yes,
Yes.
We are
ma'am.
together.
Yes.
Thank you. Now the exponential growth. So we're looking at the exponential growth. We're looking in terms of population, how the population is growing, isn't it? But then we're looking at doubling, like it doubles. That's what we're looking at. Now we have used the exponential function with base 2 to model population growth in terms of doubling time. We could also model, sorry. So they say we now have, where do I start? When we have used an exponential function with base 2 to model population growth in terms of the doubling time. We could also model the same population with an exponential function with base 3. That is when now the population is tripling, right? Time. In fact, we can find an exponential model with any base, right? If we use the base E, we get a population model in terms of the relative growth rate R. That which is the rate of population growth expressed as a proportion of the population at any time. Are we together?
Yes, ma'am.
Okay.
Yes, ma'am.
Now they say in this case, R is the instantaneous growth rate. Are we together with the word instantaneous? Guys?
Yes, ma'am.
Okay. So in calculus, the concept of instantaneous rates is given a precise meaning. Now they say, for instance, if R is equals to 0,2, then at any time t, the growth rate is 2% of the population at time t. So now they say, let's look at, okay, what am I doing? Where am I? Yay, sorry about that, guys. Now they say, for instance, if R is equal to 0,02, then at any time t, the growth rate is 2% of the population. Now they're saying exponential growth. A population that experiences exponential growth increases according to the following model. Do you see the model? Guys?
Yes, ma'am. Yes, ma'am.
What
Yes,
does it
you can
look
see.
like? What does it look like?
Compound interest continuously.
Thank you. Compound interest continuously. So it means that our money also our money, not our money, the money borrowed or the money invested, when it's compounded continuously, what happens? It grows exponentially. Do you see that?
Yes, ma'am.
So now they say a population that experiences exponential growth increases according to the model. Now NT is equals to N0 e to the power of RT, same as what we had in what's this? Continuous compounded continuously. We knew that N0 is the initial amount. Here we're saying it's the initial size of the population. And then R is the relative rate growth expressed as a proportion of the population, meaning that it'll be 0, something. And then T is the time. Now they say, notice that the formula for population growth is the same as the continuous compounded interest. That's what we said. In fact, the same principle is at work in both cases. The period of a population or an investment per time period is proportional to the size of the population or the amount of investment. Now they're saying a population of 100,000. No, I'm lying. A population of 1 million will increase more in 1 year than a population of 1,000. Is that clear? Guys?
Yes, ma'am.
Yes, ma'am.
Exactly the same way as if you invest 1 million will increase more in 1 year than investment of 1,000. That's why they're saying the richer becomes rich, because they invest millions. And then obviously money grows faster than the 1,000 rand that you invested. Now, in the next example, we assume that the population grows exponentially. So now they're saying the initial bacterium count in a culture is 500. A biologist later makes a simple count of bacteria in the culture and finds that the relative growth is 40% per hour. Now, my question is, which formula are we using? Guys?
N of T is equals to NO e to the power of RT.
Why?
Because of the relative
Because
rate of
we are
growth.
given the rate of growth.
Thank you. And the other thing, yes, thank you very much. So now they say, find a function that models the number of bacteria after T hours. Can I please have the function? Can I please have the function?
Ma'am, is going to be N of T is equals to 500 e to the power of 40 over 100 T.
E to the power of?
40 over 100. 0 is going
0.4.
Thank you. Thank you. Because remember, they said it's a proportion. So 0.4 times T. Did we lose anyone, guys? Did we lose anyone there?
No, ma'am.
No.
Not yet.
No, ma'am.
Okay. So if we didn't lose anyone, it means that we are getting there. So if we have such a question in the exam, we are fine. Okay. Now, what is the estimated count after 10 hours?
We replace T with 10, then we solve.
What's the first thing you check first? Because you will solve in the exam and then you get it wrong.
Or see if the given is are they both in hours or the other one in minutes?
Both are in what?
In hours.
There we go. So then what do we do?
We then solve.
Okay, so we then put T is equals to 500 e to the power of 0.4 times 10. Now this I can simplify up to this point. So this is e to the power of 40. Is it 40?
4, ma'am.
4, thank you. E to the power of 4. And that's how I will leave it in the exam as one of the options for the solution. Now they say, after how many hours will the bacteria count reach 80,000? Almost said $80,000. Yeah, love of money is the root of evil, toward evil. How do we solve number C? Guys, how do we solve number C? Okay, by the way, this section, a question will be there in exam. This whole entire section. I'm putting it out there. So let's participate. Let's participate. Participate, please. After how many hours will the bacteria count reach, guys? Huh?
Ma'am, I think
Oh, go ahead.
since we are solving for t, that means 80,000 is our n of t. And we're going to say 80,000 is equals to 500 e to the power of 0.4 t, then solve for t.
Okay. So they're saying that we know that, okay, let me put it here. Okay, I don't know what I'm doing now. We know that our n of t is equals to what? 80,000, which is the one they gave us here. Because they say after how many hours, so meaning that we're looking for t, right? And we know that our n of t is this formula over here. Okay, so now, I'm sorry, we know that our n of t is equals to 500 e to the power of 0.4. Is it 0.4 next? T, right?
Yes, ma'am. T.
Now we then substitute this 80,000. So 80,000 80,000 is equals to 500 e to the power of 0.4 t. You know me, I like writing the ones I'm looking for on the other side. 4t is equals to 80,000. Then divide by 5,000. Is it 500 or 5,000? Not 500. Then e to the power of 0.4 t is equals to. So how many 500 are in 80, guys? Look at this.
Just slash the zeros first.
So let's slash the zeros. And how many 80s are in there? No. I didn't slash properly the zeros.
Yeah. Supposed to
So it's okay. So what's the answer there? I know that in 1,000 I have two 5. What's this? Guys, help me.
So, ma'am, you can just say 5 into 8 is 1, remainder 3 into 30. I think that's 6. Then you take the 0.
So it's
Then
160.
Just do it bit by bit.
Okay. So now from here, what do we do now?
Since
Take the natural log.
Lin.
Thank you.
Lin.
Thank you. Since there's an e, we introduce a ln both sides. E to the power of 0.4 t is equals to ln of 160. So this is 0.4 t, which is equals to sorry, ln of 160. So divide by 0.4, divide by 0.4. Then t is equals to ln of 160 divided by 0.4. And in the exam, I would like you to, I will leave it there. Are we all together?
Yes, ma'am.
Yes,
Yes, ma'am.
ma'am.
Yes, ma'am.
Yes, ma'am.
So meaning that,
Ma'am.
let's see. So we got, okay, yes, let's see. It says sketch the graph of the function nt. Before we sketch the graph of function nt, or let's just sketch it. Do you remember exponential functions, isn't it?
Yes.
Okay. So exponential function says that if you have this, so if you have y is equals to ax, right? Meaning that your graph will look like this. And they say a is greater than 0. All your graphs will cut at 0 and 1. Do you remember that one?
Yes,
Yes.
ma'am.
Yes.
Something like this. I didn't draw it. So it will cut at 0 and 1. Right? Now look at this. We have y is equals to, not y. We have n of t. So n of t is equals to 500 e to the power of what? E to the power of 0, 4t. Ne? Now, we know that if we were to draw this graph, we'll first find the y-intercept. We know that this is t, this will become t, and this will become n of t. We first go and find the y-intercept, and we say let t equals to 0. So then n at 0, initially, where does it start? So it's 500 e to the power of 0, which is equals to 500. Meaning the y-intercept will be 0 and 500. Are we all together, guys?
Yes, ma'am.
Meaning this graph will cut here at 0 and 500 here. So let's say 500 there. That's where the graph will cut. But because we know it's an exponential function, the graph will look like this. Okay. Me, I don't know how to draw the exponential function properly. Let me draw it like this, like this. Remember, we said it approaches the x-axis but does not touch the x-axis. So the exponential function will be like this. Okay. Hey guys. Hey. Right? And then here it's 500 because we said it cuts there. Are we all together?
Yes, ma'am.
Yes, ma'am.
Yes,
But
ma'am.
then
Yes,
can
ma'am.
someone tell me the issue? So if I say this is the whole graph, what is wrong here? What is wrong here? If I say this is the whole graph, the pink one is the whole graph. What would be the issue? So this is T and this is NT. What is the issue? Can time be negative?
No, ma'am.
No.
So it means that we start here. Here. So it means that we'll only focus on this particular graph here, the upper part. Because time can never be negative. So meaning we don't look at this one. So we erase it. And that's our graph. Does it make sense or not?
Yes, ma'am, it does.
Yes, it does, ma'am.
And that's our graph.
Ma'am,
Ma'am, can
does
you
this
explain
mean,
again?
ma'am, can I ask? Does
Mm.
this mean or our graph is always gonna lie in the first quadrant?
Yes, because in real life situation, if you're modeling what's this, time in bacteria, time has never been negative. Do you understand?
Okay.
But if you
yes.
draw an exponential function, you know it will have a negative with, because here it's t0 initially up to tn, for example. But here it's negative t1, negative. Time has never been negative. So meaning that it will always lie in the first quadrant, especially when you're modeling real life situations. You can't say I traveled a negative distance. So that will apply to a negative. will apply to that as well. You can't say the population was -15. You see, so meaning that you are always right that it will be in the first quadrant because both the time as well as the population that you're looking for are both positive. So in summary, real life situations are modeled in the first quadrant. So in most cases, they'll just draw like a block like this and then remove this part, something like this. Do you see the graph?
Yes.
So we had to draw the quadrant so that we see it, we remember the exponential function. So let's see. Yes, we got that. We got that. We got that. So here in the exam, I'll give options like this, but not exact answers unless I'm able to calculate them me myself using my fingers, my toes, and then as well as my brain. Now we set n equals to $80,000. I mean, it's a population 80,000. And then solve the resulting exponential equation. Then remember we said when we see an e, we introduce the ln, and this is what we got. And then they use the calculator, and we're not using a calculator, so this is why we'll end in the exam. Here's the graph. Do you see the graph now?
Yeah.
For the radioactive decay. So we are also modeling here. Now they say the radioactive substance decay by spontaneously emitting radiation. The rate of decay is proportional to the mass of the substance. I don't know if it makes sense. Guys, do you remember proportionality? In physics, those who did physics, when they say these are directly proportional, meaning that if this one increases, this one also increases. If they're inversely proportional, it means if this one decreases, this one increases. You see, for example, exercising is inversely proportional to losing weight, because if you exercise very hard, then if exercising increases, losing weight decreases. That's directly proportional. And then eating junk food, proportional to gaining weight. So meaning if this one increases, this one also increases. So yeah, that's what proportionality means. Meaning that if the substance decays, then the mass will also what? Will reduce. So yeah, basically. Okay, let me not talk too much. This is similar to population growth, except that the mass decreases. Physicists express the rate of decay in the terms of half-life. The time it takes for a sample of a substance to decay to half its original mass. Are we together? Guys, am I talking to myself?
No, ma'am.
Now, for example, a half-life of a radium-226 is 1,600 years. So a 100-gram sample decays to 50 grams in 16 years. And then, I mean, 1,600, yeah, I'm tired, 1,600 years. And then it will decrease to 25 grams in 3,200 years, and so on. Now, they say in general, for a radiation substance with mass M0 and half-life H, the amount remaining at time t is modeled by this formula. Guys, do you remember the bacteria, the doubling? When we look at the exponential growth, when we're looking at doubling.
Yes, ma'am.
We said we say that our n of t was equals to n0 2 to the power of t over a, because it was doubling.
Yes.
And we found that this t was because of that t to the power of half. I mean 2 to the f of t. Do you remember that?
Yes.
Yes.
Yes, ma'am.
Now, here we are not doubling. This is double. We are halving. So meaning that where we see t, it's no longer t to the power of, then we have what? F of t will be a halving to the power of t. Do you see that?
Yes.
That makes
Yes,
sense,
ma'am.
guys. Now, meaning that this can be written as f of t is equals to 2 to the power of negative 1 to the power of t, which is equals to 2 to the power of negative t. Do you see that?
Yes,
Then
ma'am.
divided by h. And that's how they derive here. Are we together?
Yes.
Yes. Ma'am.
So now they're saying that. So they're saying in general for a radioactive substance with mass m0 and half life h, the amount remaining at t is modeled by this. Okay. Now, where h and t are measured in the same units, even here, to express this model in terms of mt is equals to moe to the power of rt, we need to find the relative decay. Meaning that once they give us the relative decay, we need to use something like this. Are we together? But with a negative on top there. Guys?
We are together, ma'am.
Thank you.
Yes.
So now they say, since h is a half-life, we have to find, so here we're looking for r, our relative decay. So it means that it will be expressed in terms of what? In terms of h. So this is how they did it. Okay, let me explain it on the side. So they say that we have that this, okay, here it is, the model. We have that mt is equals to m0 equals to e minus r. So they say mt is equals to m0 e minus rt. Are we all together?
Yes,
Yes,
ma'am.
ma'am.
Yes, ma'am.
Yes, ma'am.
So now, okay, what am I doing wrong here? What is it? Something is wrong here. T minus RT. So they're saying that to express this model in MT is equals to M, we need to find the relative decay, which is R, since H is the half-life. So please give me a few minutes to look at what am I doing wrong. And they say, okay, yeah, now I know what I'm doing wrong. So they say you say, okay, can I continue now? I just wanted to check what I was doing
Yes,
wrong.
ma'am.
So you're saying to express this model in terms, so we start here, right? This is where we start because of the negative side. Now, we know that T will be equals to H because that's the half-life, isn't it? The half-life.
Yes.
Are we together? So
Yes,
meaning
ma'am.
that
Yes, ma'am.
Yes, ma'am.
We'll say M of that particular half-life is equals to MOE minus RH. Are we together?
Yes, ma'am.
Yes, ma'am.
And based on what we have learned here, they say that, let's go back. They say, for example, the half-life of a radium is 1,600. So if a mass, meaning that mass at that time is 100 gram sample decay, then it decays to 50 gram, meaning that that mass will be times by what? By the current mass. That is, the current mass will be divided by 2 or times by half. So meaning that for us to find H, we then know that we can use the fact that the current mass here, after substituting the half-life, that particular time, it will be M0 over 2. Are we together? Or we can say 1 over 2 times M0, which is equals to M0 E minus minus RH. Are we together there? Yes or no?
Yes, ma'am.
Okay. So because we are looking for what? We're looking for H. No, they say we're looking for the relative, not H. What are we looking for? Okay, why am I not?
I'm looking for R,
To
ma'am.
express this, we need to find the relative decay. Thank you, the relative decay. So let's do that. So meaning that we'll divide by MO both sides. Or let me simplify it. So this is MO divided by 2 equals to MO E minus RH. So we're looking for the relative decay. So meaning that we times by 2 both sides. So it's MO is equals to 2 MO E minus RH, right? Because I'm looking for the R. So I want this whole expression to be on my right-hand side, my left-hand side, I mean. So this is 2 MO E minus RH is equals to MO. Then I divide by MO, I divide by MO. So then this is 2E minus RH is equals to?
1.
Is equals to 1, right?
1.
Now, what do I do then? I take the ln. Please help here. So, okay, so this is divide by 2, divide by 2.
First. Oh, yeah.
Minus ER. I think I'm tired now. Because what I'm doing, I don't know. So this is ln over E minus RH equals to ln over 1 over 2. So we know that, okay? So meaning here will be RH is equals to, now we can we can leave this like this if you want, but we know that 1 over 2 is the same as 2 to the power of negative 1. So we can write as ln as 2 to the power of negative 1. So then this is minus R equals to negative ln of 2. Right? So then we're looking for R, right? So then we'll divide by negative H, divide by negative H. So then this implies that our R will be equals to ln of 2 over H. Are we all together, guys? Yes or no?
Yes.
Yes, ma'am.
So
Yes,
meaning
ma'am.
that we have found R. So meaning that our M of T will be equals to M0 E minus RT. So then this will be equals to M0 E minus ln of 2 over H times T. Okay, please tell me if I confused someone because I was a bit confused myself. So let's see. So this last equation allows us to find the rate R from H. So, sorry. So then they're saying the radioactive model, if M0 is the initial mass of a radioactive substance with half-life H, then the mass remains at time T is modeled by this function here. And then R is the radioactive rate, which is the one that we found there. So meaning that on the top part, this part, you don't have to know how to derive it. You just have to know the formula because I'm not going to give you the formula sheet. So you need to know this formula and know the radioactive decay rate. Are we all together? Yes or no? Guys?
Together, ma'am.
Here's a question. How many minutes should I give you? I'm giving you 5 minutes to finish all of these questions, guys. Do we agree? Yes or no?
Unfortunately, me, I have to go, ma'am. I have to go to work. I'll watch the record.
No problem. Guys, how many minutes should I give you?
5 is okay.
Okay, I'm giving you 5. We're coming back at 14:27, and then we do it together very quickly. Okay. Now let's oh sorry. Let's start, guys. It says the polonium 210, which is abbreviated as that, has a half-life of 140 days. Suppose the sample of this substance has a mass of 300 milligrams. Find the function m is equals to m02 to the power of negative t over h that models the mass remaining after t days. What is the answer, guys? What did you get?
Yes, ma'am. So my initial mass was 300 and my half-life was 140 days. So I'm looking for a function of t in, yeah, so I got 300 times 2 of minus t over 140.
Well done. So this is m of t is equals to 300 initial times t. So this times we need to, or we can even put it in brackets so that we don't confuse it. 2 to the power of minus t over 140. Well done. The next one.
So for the next one, or should I go on?
Is there anyone else who got the answer? Let's check if anyone else got the answer. Guys, other people. Even if it's wrong, at least you tried.
For A, I
Hello,
got
guys.
the answer.
Yes, ma'am, got it.
And then for B. What did you get for B? Guys. Okay.
Okay, ma'am.
Okay, I still initial mass to be 300, but we just R, which
So
is
the initial mass is 300, yes, and then
now we have R, which is 2 over H, and is 140.
thank you.
And then
Yes.
I think we still have to solve it in terms of T. So I don't have T. I have T as a variable. Am I
So
right?
it means you are right because they say remaining after T days. Do you see that?
Oh, okay, yes, ma'am. So I
then
said M of
Mhm.
is equal to 300 multiplied by E to the power of negative bracket ln 2 over 140 multiply by T.
Well done. And then
For
now for C.
For C, they said use the find the remaining mass after 1 year. So I looked at my half-life. My half-life is in days.
Well done.
So I'm going to say 1 year is equals to 365 days.
Well done.
Then I'm going to say M of T for 1 year, which is 365 is equals to 300 to the power of E minus the ln of 2 over 140 all multiplied by 365.
Well done. So now D, what did you do with D?
I'm done, but I was using the function that I found for B to solve that because.
Okay, so let's use that function.
So I have.
So let's go back. Give me the function. It's M of T is equals to 300
e
e to the power of negative
ln
ln of 2 over
40.
140 times t, right?
Yes, ma'am.
Now they say m of t is 200.
Yes.
So this is 200 equals to 300 minus ln of 2 over 140 times t. And then, okay, me, I like writing it like this. 300 times, oh, sorry, e. So e minus ln of 2 over 140 times t is equals to 200. Now let's simplify it because I just want us to simplify it quickly because we have another one. So this is e minus ln of, sorry, in
Yes.
brackets. It's important we put in brackets minus ln of 2 over 140 times t is equals to this 0 and this 0. Let's cancel out the 0. So we remain with 2 over 3.
Yes, ma'am.
So then from this point, what did you do?
I took the natural log because of e.
Thank you. So you take the natural log because of e. So this is ln of 2 over 140 times t is equals to ln of 2 over 3. So then this is minus ln of 2 over 140 times t is equals to ln of 2 over 3.
Yes.
Now let's not simplify this using a calculator. I want us to do the way we'll do in the exam. So we know that this will be, okay, we can divide by -1 both sides so that we remove the negative. So this is ln of 2t over 140 is equals to ln of 2 over 3, but a -1. Now multiply by 140 both sides, then we have t ln of 2 is equals to -140 ln of 2 over 3 divided by ln of 2 divided by ln of 2. So meaning that t will be equals to -140 ln of 2 over 3 over ln of 2. Are we together, guys?
Yes. Yes.
So
Yeah,
let's go
together, ma'am.
back. Now the last one says how long. Okay, we've done that. So now they say draw the sample mass as a function of t time. So I think they want us to draw the sample mass, which is mt is equals to 300 e to the power of ln of 2 over ln of 2 over, what's this, guys?
140.
140, thank you, to the times h. How do we draw that one?
So do I still continue?
Yes, you can continue, my love.
Okay, so I will look for the y-intercept, which were e that h to 0, which means I'm going to have e to the
Sorry,
power.
this is t. Remember it's t, this one.
So when t is equals to 0, we have our y-intercept. So it's going to be e to the power of 0 times 300, which is 300 times 1, and it's 300. So our y-intercept is going to be 0, 300. And then
Thank then from there,
we take the graph that is on the right, I think. I have not done whether it's going up or down.
so the graph, do you think it will go like this?
No, since
No.
it's decay, the amount is going down.
Since the what?
Because of the word decay, I think, because we are going half and half and half, it will.
Okay, let's go here. Let's explain this part. Remember, I want us to always go to exponential if you don't understand the thing. Yeah. Remember, we said if you have y is equals to 2x, ne? For example, if y is equals to x, then your graph will look like this. Do you remember that one?
Yes, ma'am.
And we said that if you have y is equals to 2 to the power of minus x, which one is changing, the x or the y?
The x.
So
The
when the
x.
x is changing, it's a reflection about the what?
The y-axis.
The way
About
it
that.
is.
The y-axis, meaning that this portion will come this side, this portion will come that side. Then it will look like this. Do you see that?
Yes, ma'am.
Do you see that? Okay. Now, let's look at our graph. Our graph has an e to the power of negative something. Do you see that?
Yes, ma'am.
So meaning that it will be, we said the y-intercept is what?
0,300.
So it's here, right?
Yes, ma'am.
So meaning that because e is the, we know e to the power of a positive number, it will look like this. But now because e is what? Is a negative, it will cut here, but look like this.
Oh, that means oh, okay. I see.
Do you see that? So we
Yes.
just reflected the blue graph about the,
The y-axis.
thank you, the y-axis. Meaning that, but now because we are modeling a real life situation, we only consider the part that is in the
First quadrant.
first quadrant. Well done.
Thank you, ma'am. I see.
You're welcome. And really, it does make sense because the function is decreasing, isn't it?
Yes.
Let me put a highlight instead. So considering this part, meaning that we need to erase this part. So our function will look like this, with an arrow like this, just so that it's decreasing. So it started from 300 and it's decreasing. So it does make sense because our mass is decreasing. This is a mass and it's decreasing. So it does make sense. Initially it starts from there and then it decreases. So yes, those are the answers we got. Let's see. Those are the answers we got. But here they simplified. I didn't want you to simplify even here. Because remember, you are not using a calculator in the exam. Yes. So there's the graph. Are we all together, guys? Am I
We are
losing
together,
someone?
ma'am.
Okay. Now we have the Newton's law of cooling. Yes. Is there a question, guys?
Oh.
Is there a question?
No.
Okay. So the Newton law of cooling. They say Newton law of cooling states that the rate at which an object cools is proportional to the temperature difference between the object and its surrounding area. Do you see that? So meaning that, let's say, for example, you have coffee, right? And you put it in the fridge. The rate at which it will cool, it will depend on the temperature as well as the fridge. And you know that the fridge is more colder, right? So therefore, it means that the temperature will decrease of the coffee.
Ma'am, I think I can hear you clearly. Somebody's mic is echoing on my side.
Yes, that's Bruce's mic.
Let's see who is miking. Let me mute her. Okay. Did you understand that part, guys? Can you hear me?
Ma'am, can you just explain
Hello?
it again? Can you just explain it again?
Yes. Oh, okay. Okay. When it comes to, so with Newton's law of cooling methods, right? It looks at the rate at which something, an object cools. Do you understand? For example, if you take your coffee, or let's say your porridge, after pouring a little bit, right? If you take it and put it outside, it will cool slower compared to taking it and putting it in the fridge, right? Like in a deep freeze, for example. Guys, am I talking to? Can you hear, guys? Hello?
We can hear you, ma'am.
Okay, the rate at which an object cools is proportional to the temperature.
Ma'am, your mic.
Now, they say, provided that by using calculus, the following model can be that the Newton's law of cooling.
Ma'am,
If D0 is the initial, mute myself. Yes, can you hear
Ma'am,
me?
we can't hear you. We can't hear you, ma'am.
Let me see. Can you hear me now? It might be the network. Okay. Oh.
I think she's trying to reconnect again.
Oh, okay.
Can you guys hear me now? Hello?
Yes,
Oh, thank you.
ma'am.
yes.
Ma'am, we can hear
Yes.
you.
Network was acting up. I do apologize about that. Okay. So now they say that, did you understand when does the Newton's law of cooling comes in? Let's start there. Guys?
No, no, ma'am.
So here they're saying that the Newton's cooling states that the rate of change of an object's cooling, meaning
And
that
we
if
can't
you
see your screen.
you let me know when you can.
We can.
Thank you. So they're saying here, the Newton's law of cooling state say that the rate of which an object's cooling, meaning that the rate at which your coffee is cooling from hot to cold, is proportional to the temperature difference between the object and its surrounding. Does it make sense?
Yes, ma'am.
So provided that the temperature difference is not too large. Now, by using calculus, the following model can be deduced from this law. They say Newton's law of cooling. If D0 is the initial temperature difference between an object and its surrounding, meaning that if the temperature of the coffee minus the temperature of the surrounding, let's say the temperature of the fridge, if you put it in the fridge, and then that's D0, right? It's the difference. You take the temperature of the coffee minus the temperature of the fridge. And if its surrounding has a temperature Ts, now in this case, Ts will be the temperature. Then the temp of the surrounding, meaning in this case, if we're looking at coffee and fridge, then Ts is the temperature of the fridge. Then the temperature of the object, that is time T, is modeled by the function this. Meaning the temperature of your coffee, let's say after 2 minutes, if you have put it in the fridge, therefore it will be given by that model. Are we all together?
We are together.
So they say where K is the positive constant that depends on the type of an object. Sometimes, guys, it might be gold cooling, for example, a metal cooling or a mineral cooling. It doesn't necessarily have to be like water or something else. It can be your soup cooling even. So now they say, oh, here they use the cup of coffee. So now they say a cup of coffee has a temperature of, we'll use degrees Celsius because we normally use that. So let's say a cup of coffee has a temperature of 200 degrees Celsius and is placed in a room that has a temperature of 70 degrees Celsius. After 10 minutes, the temperature of a coffee is 150 degrees Celsius. Find a function that models the temperature of a coffee at time t. How many minutes am I giving you? 5 minutes. 5 minutes to try it. Look at the model. Guys, let's look at the model, and then I'm giving you 5 minutes to try the question. Is that okay?
That's fine.
Yep.
Okay, please try the question. And then I'm giving you 5 minutes. So it means we're coming back at 34, 35, 30, I mean, what I'm saying, 53, 54, 58, 1458. Then we come back and do the corrections.
Ma'am, please return to the question.
Ma'am, just to be sure, we said DO is the difference, right?
DO is the initial.
What?
The difference is the initial temperature difference between an object and its surroundings.
Okay.
How far are you guys? Sorry. How far?
I'm at B.
Okay, let's do quickly so that we finish this part. How far, guys? How far are you? Can you hear me?
Yes, ma'am.
Let's see.
We had C, ma'am.
Okay. Do see then so that we can finish with this one and then we'll be done for the class today. Please tell me when you're done.
I'm done.
Also done.
Guys, I've been talking to myself and no one is saying anything.
I said we were done.
Because now I'm explaining here. Okay, please help me then. Let me not explain it. Please help me. So how do we go about? So this is where we start, because here we can see they're talking about a coffee and it's cooling and whatsoever. Here, right? Now, how do we find D0?
It is the difference between the the temperature of a coffee and of the room.
Thank you. So meaning that, let's say TC, let's call it temperature of a coffee, ne? So let's say temperature of coffee. Then we know that D0 is equals to temperature of coffee minus temperature of the surrounding, which is the temperature of the room. So now we know that the temperature of the coffee, okay, let me write it here. We know that the temperature of the coffee is equals to what? 200. And the temperature of the surrounding, yes? Is there a question?
Continue. Continue, ma'am.
No. Okay, now the temperature of the surrounding is 70. So then this is equals to 200 minus 70. This is equals to 130. Are we all together?
Yes.
So meaning we go and substitute. So then we have T of T is equals to, now we know TS is 70, so that's 70 by 0, which is 130, e to the power of minus K times T. Are we together there?
Yes, ma'am.
But we are not done. Then go back to the formula. And they say where K is a positive constant that depends on the type of object. Okay? Now, they say that, look at this, there's an additional statement that can help us to find K, because here we want to find a function that models the temperature of the coffee at time T. And this cannot be the function because now this is a function of K and T, and we want it to be only the function of T, meaning that we also have to go and find the value of K. So now how do we find the value of K? We then go check on the statement and see, are we given more information? Yes. After 10 minutes, are we together there, guys? After 10 minutes, what happens after 10 minutes? The temperature of the coffee is what? It's 150 degrees Celsius. Does it make sense?
Yes, ma'am.
So they're saying that this statement can actually help us to find the value of K, because they're saying at T is equals to 10. So they are saying at T is equals to 10, then T of 10 is equals to 150. Meaning we can substitute here and it will help us to find the value of K. So then we can say a T of 10 is equals to 70 plus 130 e to the power of minus K times 10. We know that this, if you substitute 10, we have to get 150. So then we'll have 70 plus 130e minus 10K, which is equals to 150. Then we can simplify 130e minus 10K is equals to 150 minus 70. So 150 minus 70, guys.
80. 80.
It's 80, and then we divide by 130 this side, we divide by 130 this side. So then we have e to the power of negative 10K to the power of negative 10K. So this 0 and this 0, so 8 over 13. Can simplify there further. Then what do I do from here?
You introduce
a ln.
Thank you. So then we say ln of e to the power of negative 10K is equals to ln of 8 over 13. So we don't have space anymore. So then we have that e to the power, okay. So e to the power of minus 10K is equals to 8 over 13. Introduce the ln, so e minus 10K is equals to ln of 8 over 13. So this is minus 10K is equals to ln of 8 over 13, meaning that K is equals to minus ln of 8 over 13 over 10. Are we all together there?
Together, ma'am.
Yes, ma'am.
So then we have found our K. So we then go back to our formula, which says T is equals to 70 plus, yes?
I have a question.
Mm.
Here we have found our K to be negative, but didn't what was that? The definition say and K is a positive constant.
How? You're saying what? Oh, sorry. You mean the definition?
Yes.
Okay. What might happen is that this inside here will be positive. If you take ln of 8 over 13, it might be negative to make K positive.
Oh, okay.
Let me see. Let's do that and see. Let me see if they say yes. When it should be like that. So if you say ln of 8 over 13, it should give you a positive answer.
Okay, ma'am.
Please check. Can anyone check with the calculator? Whoever has a calculator next to them. So ln 8 over 13 should give you a negative answer such that it cancels that negative or in front. Please check that.
Yes, ma'am, it is negative.
Thank you. So then it becomes negative something times this one here, and then it becomes positive. Thank you for highlighting that K has to be positive. Okay, so then let's go back to the definition. Okay. So it'll be positive. Do you see now that, okay, do you see that K is negative, ne? I mean, K is positive, such that when you substitute here, it will model the graph, and the graph will be a decreasing function because your temperature is decreasing. So in mind, do you have a picture of how your graph will look like, guys?
Yes, we do, ma'am.
So let's go back. So this is what? So this will be now minus, it will be positive because it's minus ln of 8 over 13 over 10 times t. So this is equals to 70 plus 130 e. This minus will be what? Positive. So then we'll have ln of 8 over 13 over 10 times t. Are we together, guys?
Yes, ma'am.
Let's draw the graph from before that, let's draw the graph from this. We are just jumping the step. Can one say something? What would be the power, positive or negative? This power here.
Come again.
This power here, will it be E positive or E negative?
E negative.
Why?
Since the ln of 83 was a negative number.
Thank you. So it will be E negative because if you look at like this, you will think that it's positive and then your graph will end up looking like this. Do you see that? And then it means you are wrong. Does it make sense, guys?
Yes, ma'am.
Yes.
So now let's draw this graph. So let's start from exponential. From our exponential, we said we had, if we have like this, AB, okay, let's say, yeah, ABX plus Q. Ne? We said this is our horizontal asymptote, meaning that the graph will be close to this, but do not touch it. That's what we said, right? So now if you draw that graph, you first go and draw this horizontal asymptote. So this is why this is X. So this Q, let's say if it's positive Q, it means it will be here. This is Q. Do you see that? And then it means now this is your asymptote because initially when we had a graph of just y is equals to a to the power of x, your graph, your horizontal asymptote was the x-axis, meaning your graph will be close to the value but do not touch the value. Are we together there?
Yes, ma'am.
So
Yes,
now,
ma'am.
meaning that here, this is q. So if this is positive, meaning that if we have y is equals to a to the power of x, then your graph will be like this. Okay, let me remove this part here. Then your graph will be like this. Plus q. Your graph will be like this, will be close to q but does not touch q. Now, if we have a y to the power of a to the power of negative x plus q, do you see that now you are reflecting about the x-axis, I mean the y-axis. Now your graph will look like this, but do not touch what? Do not touch q. Do you see that?
Yes, ma'am.
Thank you. So now, it means that if we come to here, this exponential function here, what is our horizontal asymptote in this graph? Hmm?
70.
70.
70.
So meaning that you're going to draw here and say dot, 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 70. Let's say 70 is here, right? Now, your graph, would it look like this one? Let's call this graph 1, or it will look like this one, graph 2.
Graph 2.
Graph
Okay?
2.
Thank you.
Graph 2.
Now, where is the y-intercept?
Zero comma 300.
130.
130.
0,130.
200.
200.
Zero
Someone say 200. Someone say 200. They are right, because remember, we let t equals to 0. So then this is 70 plus 130 e to the power of 0. Isn't that when you put 0 here, everything becomes 0?
Yes.
So then this is 70 plus 130, which is equals to 200. Meaning that, let's say 200 is here. Do you see that?
Yes, ma'am.
Now, because you know your graph will be like this, but will not cut. Do you see that? Now, because we know that we are dealing with the positive part, we are dealing with the real life situation. Now, this will not be y, it will be tt, and this will be the time. And because we know time cannot be negative, we're only dealing with this graph here in the first quadrant, meaning that the entire graph, we need to remove it. And then we are dealing with only the positive part, which is this part and this part, meaning the pink part we remove like this. Can remove this part here. Do you see that, guys? And that's your graph.
Ma'am, can I ask
Mm.
why we say this graph is a negative graph?
We're not saying the graph is a negative graph, right? But we are showing that the graph, whatever we are modeling, is decreasing. And yes, the temperature of a coffee after some time, let's say initially when you boil water, it was T0, right? It was here. Ne? Now, after 5 minutes, temperature will decrease, obviously. Do you see that? Ne? Now, the reason why we're saying it's negative, you meaning, why are we saying it's a negative value graph, something like that?
Yes, something like that.
It's because, look at this. If you take ln, if you take this value, you say ln of 8 over 13 in a calculator 10, it will give you a negative value. let's say negative A, especially this part, it will give you a negative value. Do you see that? So meaning that if you substitute in your equation, it will be TT equals to 70 plus 130 e to a negative 80. Do you see now that negative comes in? That's why then we show that the graph will be like this.
Okay, okay.
Okay. Where am I now? Okay. So now they say after temperature, what is it? Find the temperature of the coffee after 15 minutes. What do we do? So we found, let's see. Okay, we find our T to be this one. But remember ours was not written like this, where we didn't simplify the, so our T was this one here. So after 15 minutes, what do they mean? So here there was a T. And then let's go back. After 15 minutes, you check. You see that, oh, okay, fine. After 10 minutes, meaning that we're actually working in minutes. So then you take your T and substitute T is equals to 15. Are we all together there, guys? Is
Yes.
that what we did?
Yes, ma'am.
Okay. So meaning that in our equation, this one over here, we say T of 15 is equals to 70 plus 130 e to the power of ln of 8 over 13 divided by 10 times what? Times 15. And then you substitute there. That's how you get your answer. Are we together?
Yes, ma'am.
So to find the exact temperature of this, it means you have to substitute in a calculator. But because we're not using calculators, I want you to actually come up to this point in the exam. Be able to understand up to that point. Now they say, after how long will the coffee cool to 100 degrees Celsius? So meaning that now they want to find time. Are we together? Guys?
Yes.
Yes.
Yes,
Together,
ma'am.
ma'am.
Meaning that they want us to find T. They know T is equals to what? 100. Meaning that we're going to say 100 is equals to 70 plus 130 e to the power of ln of 8 over 13 over 10 times T, right? So then what we do is we then simplify. So, you know, I like writing it like this, 130 e to the power of ln of 8 over 13 over 10 times T is equals to 100. So let's simplify that. We know that this will be 130 e to the power of ln of 8 over 13 over 10 times T is equals to 100 minus 70. So this is 130 e to the power of ln of 8 over 13 T divided by 10 is equals to a 13. Are we following, guys?
Yes, ma'am.
Yes, ma'am. Yes.
So
Yes,
then
ma'am.
divided by 130 this side, divided by 130 this side. So then we left with e to the power of ln of 8 over 13 T over 10 is equals to that zeros cancel. So we have 3 over 13. Altogether up to that point.
Yes.
Yes.
What do we do from here? I think now we know how this is go. What do we do from here?
Introduce.
Introduce the
Thank you. Let's do that. So we know that E, okay, so it's e to the power of ln of 8 over 13 divided by 10 times T is equals to 3 over 13. We introduce the ln, so this is e to the power of ln of 8 over 13 divided by 10 times t is equals to ln of 3 over 13. So then we know that we remain with ln of 8 over 13 divided by 10 times t is equals to ln of 3 over 13. So meaning that times 10 both sides, because we want to cancel 10 on the left. So this is ln of 8 over 13. T is equals to 10 ln of 3 over 13. Now there, we divide by ln of 8 over 13 over ln of 8 over 13. So then t is equals to 10 ln of 3 over 13 over, what's this, ln of 8 over 13. Are we together, guys?
Yes.
And
Yes,
that's where
ma'am.
you
Yes,
can,
ma'am.
so that's where you
Yes,
can
ma'am.
leave your, please go and check if what we did is correct. If it's not, we then have to fix it. But all the steps that we have that we have done so far is correct. So let's go. Actually, we found this one. We are right. That's what we got. And that's the value of k. So we ended here. This is where we ended, right? The value of k, and then we went and substituted k. So here they simplified it. That's why they can see a negative. For us, we didn't simplify it. But if we take ln of 8 divided by 13, we noticed the negative. And this is what we got. You see, C is was actually what we got. So this is ln of 3 over that. This is what they got. Okay. Now the issue is that, okay, they simplified it using a calculator, so we didn't. Okay. Now this is the graph that we drew. Do you see that, guys? This is the graph we
Yes.
drew.
Yes, ma'am.
And that was our last session. Last slides. So guys, those who said they don't understand how to draw graphs, can you please send me which ones are you talking about? Because we need to simplify. Let me stop the recording. Was I recording? I hope I was recording. We need to be able to then work together so that we understand how to draw the graphs. So